So today I'm just going to review another one of these exercises here, and then I'm going to do a few quizzes as well. So I don't know, like based on the name, custom hasher, obviously something related to hash, but I don't know what this is yet. Is the next one on the list here. It just uses this slice from raw parts. Here. So obviously based on the name, I think it's gonna slice something. A pointer, probably, based on this. These macros, as always, is kind of weird because I think that I can't go all the way to the definition. There's some stuff that gets hidden based on the compiler, I think. I already asked GPT what it thinks about the solution, but I want to manually skim first or review to see if I understand what is going on. I don't want to take time to read the comments there. It is kind of annoying that you can't look into the all the logic for everything. Obviously, at some point, I think it's probably a good idea. I should write down next time that I watch Rust videos or people talking about Rust. The books are very good, and on the books there are some resources that talk about these things. There are papers as well. I have a bunch of them here that I'm reading. And one of the names that I saw there as well now is Miri, or however you say that, which I think has something to do with the compiler internals, and then there's another name which is called Salsa, I think, or something like that. It's also related to the compiler internals. You should probably study. From what I understand roughly, you have a system where they have logic that allows them to set a goal for the compiler, and then the compiler tries to solve the types or something like this. But this stuff here, as I talked with ChatGPT at some point, is more on the intermediate representation. I think that the compiler creates something, like some intermediate representation code that goes along the LLVM intermediate representation, and then that code adds the logic for this kind of stuff. So it's not really fully Rust, it's the compiled version into the intermediate representation that adds a lot of this logic here. And that's why it doesn't show on the files, I think. So the only way is to look into the Rust implementation, I think, the Rust C implementation, which is the Rust compiler. But basically judging on this, so here is going to implement the straight for the integer type, which is built-in type. So it's going to get the bytes of the type as a pointer, and then the memory size. And it's going to slice, I don't know what that means. I'm going to search on the docs as well, what the standard slice from raw parts does, the Rust documentation. There is a way, I think, as well to quickly look into the Rust docs locally. Should probably study that as well. It's cargo doc or something like that. Okay, so I found
Skip to main content settings help from function from underscore parts 1.0.0 const 1.64.0 source search settings help with const unsafe fn from underscore parts a t data const t len usize a t forms a slice from a pointer in a length. The len argument is the number of elements, not the number of bytes. Safety behavior is undefined if any of the following conditions are violated. Data must be non-null, valid for reads for len size underscore of t many bytes, and it must be properly aligned. This means in particular, the entire memory range of the slice must be contained within a single allocation. Slices can never span across multiple allocations. See below for an example indirectly not taking this into account. Data must be non-null and aligned even for zero-length slices or slices of DSTs. One reason for this is that enum layout optimizations may rely on references, including slices of any length, being aligned and non-null to distinguish them from other data. You can obtain a pointer that is usable as data for zero-length slices using non-null dangling. Data must point to len consecutive properly initialized values of type t. The memory referenced by the return slice must not be mutated for the duration of lifetime a, except inside an unsafe cell. The total size len size underscore of t of the slice must be no larger than size max, and adding that size to data must not wrap around the address space. See the safety documentation of pointer offset. Caveat: the lifetime for the return slice is inferred from its usage. To prevent accidental misuse, it's suggested to tie the lifetime to whichever source lifetime is. Safe in the context, such as by providing a helper function taking the lifetime of a host value for the slice, or by explicit annotation. Examples use std slice manifest a slice for a single element let x42 let ptr x is const underscore let slice unsafe slice from underscore parts ptr 1 insert underscore eq. Slice 0, 42 indirect usage of the following join underscore slices functions on sound warning use std slice fn join underscore slices a tfst ft snd ft a t let fst underscore end fst as underscore ptr wrapping underscore fst len let snd underscore start snd as underscore ptr insert underscore eq fst underscore end snd underscore start. Slices must be contiguous. Unsafe the assertion of ensures fst and snd are contiguous, but they might still be contained within underscore different allocations underscore, in which case creating the slice is undefined behavior. Slice from underscore parts fst as underscore ptr fst len snd len f and main and d are different allocations. Let 42 let b27, which may nevertheless be laid out contiguously in memory. Of let underscore join underscore slices slice from underscore fa slice from underscore f bf fi handling null pointers in languages such as C++. Pointers to empty collections are not guaranteed to be non-null. When accepting such pointers, they have to be checked for nullness to avoid undefined behavior. Use std slice on the elements of an FFI slice. Safety if ptr is not null, it must be correctly aligned and point to len initialized items of type f32. Unsafe return cfn some underscore slice ptr const f32 len usize f32 let data if ptr is underscore null len is assumed to be 0. Else safety see function doc train. Unsafe slice from underscore parts ptr len data into underscore there. Some this could be the result of CSSTD vector data. Let ptr std ptr null and this could be std vector size. Let len 0 assert underscore eq. Unsafe some underscore slice ptr len 0.0.
I'm not sure if I understand the concept. For me, naturally, it makes more sense to think about a slice as a part of something, obviously. But here it seems that it is creating like the region of memory, like the whole thing, but it's called a slice, so it's kind of confusing. That's what it seems to me that's happening here, just based on the names and the that is being called. Like we pass the pointer to the bytes of this implementation, and then you pass the size of. Not sure if it should be the size of the whole thing as well, of all the bytes, because I think that's what it means here, because implementing for i32, so we're gonna get the bytes for that i32, and then you get the size of that i32, I think, and then this creates a region in memory for that, I think. That's what's going on here. There's just a macro and another macro here. There's a comment there. Right, so it returns a fixed array which lives for the lifetime of self. A fixed array using little endian guarantees consistent hash values across all architectures. Okay. Yeah, so it's basically what I think is happening here. It's just gonna, it's kind of like allocating an array but directly on memory. Like directly using the memory, built-in memory structures on Rust instead of using a pre-built or a built-in data type. Condition. I think this is just a check, and this is probably the main logic. So that's the address of the points lies from the data is the bytes and the length. Obviously the size. Then I can't look into this. Yeah, I assume that the actual functionality is going to be done on the macros, which only happens, as I explained before, on the intermediate representation thing. Yes, bounds within whatever. Lowers in. Yeah, this is the name I was thinking about. Miri, however you say that, is used to implement functions like slice from useless. When compatible with the compiler being able to change the possible layouts of pointers. Okay, so let's move on. So it does the same thing for strings here, but assume it's basically probably gonna be the similar functionality under the hood, but just for strings instead of the i32. It's basically allocating the bytes in memory for that type. Then it has this hasher and a hash function. And then this is similar to the hash map one, but there is no shift here. But I think the rest is basically very similar or like almost the same. Yeah, here there's the hash, and then it adds by the hash, which is this value here. But here is adding by 33. So it's pretty close to the same thing. I assume obviously it can depend on the implementation, what hash you're gonna use. And there's different hashes here. Then there's a node, also very similar to the hash map. It is basically a hash map. I think it's a hash map that allows you to initialize with a custom hash you want. The hasher is here, then it implements these two different hash maps as an example. Also by default is initializing with this one. But I guess you could call the method directly there instead of calling new. You can basically use any hash you want. I think it's a hash map where you can use or you can select what hash you're gonna use for the hash map. That's what this is. So there's the growth function here. Slightly different than the other hash map implementation that I've seen, which accepted the rate of growth, I think. It's a lot easier to understand the implementation than to rebuild it. I don't think I can rebuild myself without looking at the solution and without looking at documentation either. Obviously, with enough time, I think I can do it. With enough time and looking into the documentation, then I think I can do it. But it wouldn't be easy, I think. There's a lot of stuff to remember, like these little details here. It's easy to read, but it's very hard to build from scratch. This is a pattern that I've seen in all the other ones where they use this layout, and it's like just a manual way of allocating memory, and there's something about the dropping logic, or they initialize the memory this way because then it doesn't have to assume a type, I think, when you initialize. Because if you use something else, then the compiler automatically assumes the type on the memory region. Or something like that. It has to do with the drop semantics, I think. It doesn't allow me to see the actual thing. The magic symbol should call the global allocator, Rust generates them to call the global. Blah blah. I guess I can ask GPT again and then look into the documentation again to see why they do it like this. Remember. So that's the pattern that all of them follow. To create a layout, the specification of the memory region you want. have the capacity, which is the size, obviously. Then the type determines the structure of each value, I think. And then you use alloc, which is Rust built-in type to manage memory. And that function specifically is probably gonna allocate with all values to initialize to 0, I think. And here's basically the same as the hash map and obviously the hash set as well. It just creates these buckets. And I think that the main reason for the bucket is the collision handling. So when you create a key on the hash map, it's gonna use that key to call the algorithm that is gonna create the hash, and that creates the linking space. Like it creates the memory address of the value, I think, when you hash with the key. So you pass the key to the function does the algorithm that it has there, depending on which hash you are using. Then the result's gonna be an address, and that's the address where the value is at. But then you could have the situation where you get the same address for a different key. So you need to differentiate both. And that's when you have this index here. And that's what's going on. Yeah, so the hasher is going to hash based on the key bytes. So the key is the type, which is either an integer or a string because of the implementation there before. And this function is going to get the actual bytes of the thing. Then it passes through the hash. Then it does this module for the capacity. It should wrap around. The module I've seen on ring buffer as well. I think it wraps around the address so that it doesn't grow forever, I think. So then if you hit the same space, then you need to do this traversal here, which is going to basically create a linked list between the values, I think. So first makes it mutable by the current here, and then it traverses the nodes. Until it finds the key. Not really, it's kind of weird though. Because here it seems that it would replace the existing value with the new one, which is kind of weird. Because the keys are obviously going to be the same whenever you have a conflict. So, you understand. That is kind of weird. Maybe GPT will say something about this. Because if the keys were different from each one, then like it wouldn't make sense to have this linked list for the collision. Like it only makes sense if you're gonna place on the same spot. So I'm gonna ask that to I'm gonna ask GPT to explain, I think, what is going on. So the rest, like just roughly looking at it, it seems pretty much the same as the other ones. We have the drop implementation. The drop usually you don't have to delete. If you use the value, then Rust automatically drops the value after. So usually on the drop implementation, that's how they're gonna do it. They just use the value and then it drops automatically. And this is basically the same thing that you have on C++, where the language itself has built-in types, and then this like special built-in types allow you to change the behavior of other built-in types. That makes sense. So C++, I think you have iterators, where if you declare an iterator inside of a class, for example, or something like this along those lines, then it allows you to determine what happens as you're looping over that class. You're basically telling the compiler how to manage the memory, I think. So in Rust is basically the same idea. The drop implementation determines what happens when the value of the thing you are creating goes out of scope. So when you use the hash and this hash goes out of scope, it's going to implement this algorithm here. Is the function. The rest is just tests. So I'm gonna read the GPT's comments here, and then I'm gonna ask. Yeah, I'm just gonna ask the question about to explain what happens inside of that loop there, because I don't understand. Kind of symmetrical, so maybe when I understand the insert, I'm gonna understand the remove by taking directly. Maybe I ask both.
I would not accept this solution unchanged. The core separate chaining hash table logic is mostly reasonable, but there is one genuine memory safety bug, plus several design and testing issues worth fixing. One critical, key bytes for i32 returns a dangling slice. This is the biggest problem. Rust self to underscore l underscore bytes, but as underscore ptr to underscore l underscore bytes creates a new temporary u84. The pointer points into that temporary, not into self. Then, Rust std slice from underscore raw underscore parts manufactures a slice whose lifetime appears to match self, but the array backing it is destroyed when the expression slash function finishes. So this comment is incorrect. Rust safety to underscore l underscore bytes returns a fixed size array which lives for the lifetime of self. It absolutely does not live for the lifetime of self. The return u8 is dangling, and reading it is undefined behavior. This is also an excellent example of why unsafe deserves unusually precise safety comments. The compiler allowed you to claim a lifetime the underlying allocation did not possess. The deeper problem is actually the trait. Rust trait key bytes underscore bytes self. U8 this interface means the bytes I return already exist somewhere inside, or otherwise live at least as long as self. That works for str because as underscore bytes stores existing storage. It does not naturally work for i32 because converting it to a chosen byte representation creates new storage. I would redesign the abstraction rather than trying to patch the unsafe implementation. For example, have the key feed bytes into the hashing operation, so an i32 implementation can safely do Rust-like values. Self to underscore l underscore bytes hasher the hash bytes while bytes is still alive, or more idiomatically, model this after Rust hash slash hasher relationship. To the resize threshold is slightly wrong. You have Rust if self len 4 self cap 3 self row capacity 16 len 12 48 48 is false insertion occurs len 13 load factor becomes 13 16 81.25 so despite the comment referring to 0.75 the map is allowed to exceed 75%. If the intended invariant is load after insertion 0.75 you need to consider the perspective length. There is another related issue. Resizing happens before determining whether the key already exists. Suppose the map is above the threshold and you do Rust map. Insert existing underscore key new underscore value len 1 increase yet you'll resize anyway. A structure insertion conceptually is look for an existing key. Replace and return if found. If this is actually a new entry, decide whether growth is necessary. Insert it. 3 the load factor arithmetic can overflow. Use can overflow. Rust self. Len 4 self cap 3 in this 2. Rust let u underscore cap 1 underscore cap 2 you probably won't reach those values in an ordinary program because allocation will fail first, but an exercise explicitly teaching allocation in low level. Correctness should acknowledge integer overflow. Check underscore null is appropriate for the capacity increase. This matters less operationally than the dangling i32 slice, but it's exactly the sort of invariant worth teaching. In a manual container exercise, for grow is not panic safe. This is subtle and interesting. You start physically removing nodes from the old table. Rust let make yourself. Buckets dot add update and then call user provided code. Rust self the hasher the hash node key underscore bytes because hasher is a public trait. That implementation can panic. If it does, you potentially remove nodes from the old map, inserted some into new underscore buckets. Left self the buckets pointing to the old array. Left self. Len unchanged. Leak the new raw allocation. Potentially dropped entries that were detached but not moved. It isn't necessarily UB, but after detached underscore unwind the map can be logically corrupted and raw memory associated with the temporary table can leak. For an introductory exercise, I wouldn't necessarily demand strong panic safety, but I would document it or design around it, especially because you intentionally made the hasher pluggable. An important low-level container lesson is once you begin mediating ownership structure, avoid calling arbitrary user code unless you have a rollback / RAI strategy. That applies to hashers, comparison implementations, destructors, callbacks, etc. 5. The key contract is missing an essential invariant you require. Rust KEQ key bytes, but there needs to be a contract equivalent. 2. A b hash be more specifically for this abstraction. A b underscore bytes and b underscore bytes produce equivalent hashing, but otherwise the user can legally implement both traits according to their individual signatures while making the map fail. For example, imagine equality ignores case. Foo but key underscore bytes preserves case. Equal keys can then go into different buckets and lookup stops working. Rust standard hash trait has exactly this relationship with EQ, and it's a very important hash table invariant to learn. 6 hash map generic over hasher is technically inaccurate. The comment says Rust hash map generic over hasher, but it isn't generic over the hasher type. Rust obstruct hash map k v hasher box hasher gets using dynamic dispatch through a trait object. A genuinely generic version would conceptually look like Rust hash map k v h with Rust h hasher. The distinction is worth teaching because the trade-off is meaningful. Your version introduces a heap allocation for the hasher, virtual dispatch, no hasher inlining, runtime rather than compile time hasher selection. For the exercise, either design is defensible. I would just describe it correctly. 7 your custom hasher is quite different from Rust real hasher. Calling this Rust pub trait hasher can make the exercise slightly misleading because std hash hasher has a different model. Rust ecosystem essentially uses hash downward arrow feeds values into hasher downward arrow produces hash build hasher downward arrow constructs hashers for hash map your abstraction. Is instead a one shot. Rust bytes use 64 that's perfectly fine for learning hash functions, but I would either name it something like byte hasher or explicitly explain the distinction. That would make the exercise teach both how the simplified hash table works, how the standard library generalizes the idea. 8 the so-called collision test does not test collisions. This test Rust this underscore collision underscore with underscore different underscore hashers doesn't cause or test a collision. It inserts one key into 2 completely separate maps. Rust map 1 insert a 1 map 2 insert a 1 that's essentially another hasher selection test. For this data structure, collision tests are among the most important tests because collisions exercise your linked list implementation. A perfect test hasher would simply return a constant hash anything 0 then insert several distinct keys. A bucket 0 b bucket 0 c bucket 0 now test get head get middle get tail overwrite middle remove head remove middle remove tail remove non-existent key len after every operation. That actually validates the difficult part of the implementation. 9 growth needs dedicated testing. None of the current tests really verifies row. That's particularly important because growth performs the most dangerous ownership manipulation in the entire implementation. I force multiple resizes and verify every entry survives. Insert 0 1000 verify 0 1000 remove some verify remainder you want to detect. Lost nodes, duplicate nodes, indirect rehashing, bad len, broken chains. For a hand-built data structure, tests should specifically attack every ownership transition. 10 updating an existing value deserves a test. You return the old value here. Rust some stdmem replacement node. Value that's good behavior, but isn't tested. You want the invariant. Insert K. A. None insert K. B. Some len1 get KV len1 part is especially important. 11. The raw allocation itself is mostly reasonable. This portion is actually decent. Rest layout array. Option box node K. V cap alloc underscore 0. Handle underscore alloc underscore error. And the corresponding delocation uses the same element type and capacity. The iterative destruction is also a good choice. Rust while it's somewhat node node. Next update it prevents relying on recursively dropping an arbitrarily long linked chain. One teaching improvement I made is to more clearly document the invariant surrounding Rust buckets. Mud option box node K. V something like buckets points to an allocation for exactly cap elements. Every element 0 cap is initialized. Every element contains a valid option box node KB. Hash map exclusively owns the allocation. Allocation layout corresponds to cap. That's the real foundation that makes every subsequent unsafe reference valid. 12. Node probably shouldn't be public to expose. Rust pub struct node K. V pub key. K. Pub value. V. Pub next. But users cannot access the maps buckets anyway, so this unnecessarily exposes the implementation representation. I normally make it private unless examining / manipulating nodes is explicitly part of the exercise. It's a useful API design lesson. Public types become promises about implementation structure. A hash map shouldn't normally promise that it uses linked list chaining internally. 13 DJV2/FNV1 are fine here, but not a production default for the exercise. They're excellent because the algorithms are simple enough to understand completely. DJV2, H33 byte end, FNV1A, H byte H prime. That's good educational material, but neither should generally be your default hash table algorithm when keys can come from hostile / untrusted input. Their collision behavior is predictable, which can permit deliberately constructed collision attacks. A real Rust application would generally start with Rust STD collections hash map and its build hasher, or deliberately select another hasher when performance / security requirements justify it. So I keep both algorithms in this exercise. What you should learn from this solution, the most important lesson, is actually DJV2 or FNV. It's the layering of invariants. Hash map raw bucket allocation exactly cap initialized bucket values. Bucket invariant option box node ownership invariant. Every node belongs to exactly one chain hashing invariant equal keys hash compatibly indexing invariant hash cap. Is always with an allocation length invariant len total number of nodes resize invariant. Every old node moves exactly once, and this solution contains a particularly valuable unsafe lesson. Rust from underscore raw underscore parts pointer. Len doesn't merely say these bytes exist. You're asserting several facts simultaneously. Pointer is non-null required. Pointer is directly aligned. Len is valid. Memory is initialized. Memory remains alive. Aliasing rules are respected. The resulting reference has a valid lifetime. The I32 implementation satisfies the first queue temporarily but fails the lifetime requirement. That's exactly the kind of bug exercises using unsafe Rust should teach you to recognize. Where this appears in a real Rust project, you would almost never handwrite this general purpose hash map in application code. You'd use STD collections hash map, but the individual techniques appear constantly in systems work. Manual bucket / storage management like this appears in custom allocators, memory pools, arenas, ECS storage, caches, specialized hash tables, game engine internals, embedded systems, databases, runtimes, lock-free structures, and FFI backed containers. The hashing abstraction appears in compilers, databases, caches, content address storage, interning systems, deduplication systems, symbol tables, graph systems, and specialized lookup tables. And the most transferable piece is the raw memory reasoning. When building serious Rust infrastructure, you'll repeatedly encounter the same question: what exactly is allocated? Who owns it? Which elements are initialized? Which references can exist? What happens when ownership moves? What happens if something panics? What must be true before delocation? That's the real value of reconstructing a hash map this way. Assessment area assessment basic hash table algorithm good separate chaining good insert /get /remove logic mostly good growth. Algorithm conceptually good. Needs robustness. Raw allocation / allocation mostly good. Key bytes for I32 and sound / must fix overflow handling needs improvement. Panic safe times improvement. Collision testing missing resize. Testing missing API abstraction useful but somewhat misleading educational value high after fixing the lifetime bug. The one change I would consider mandatory before marking the exercise complete is redesigning key bytes. So numeric keys cannot return references to temporary byte arrays. After that, I make genuine collision tests and resize tests the next priorities.
But something I remember as was talking about the hash here, the algorithm is that the built-in type, the built-in hash map on Rust, they implemented an algorithm that because an issue can be that if someone knows the hash map algorithm, they can create a denial of service attack because of the way that the hash is gonna allocate the memory. So they had a problem with this, I think, on Rust, and so that the built-in type uses a special kind of hash algorithm, and I think that for that reason is not completely open either, from what I remember as well. But then that hash algorithm prevents this type of attack as well. So I'm just gonna ask the question about. I'm gonna ask it to explain what is going on inside of the loop there. Well, as it responds, I'm gonna start doing some quizzes. Okay, so I think that this one is receiving as a reference and is mutable, so I think it is gonna pass and it's gonna be true. If it wasn't a reference, then it would drop and then it would collapse here. So the references adds one. Also, the reference must be marked as mute. Didn't realize that, but that's kind of weird though. Because it is mute here. I don't understand this actually. Oh, actually, I think that you need to put mute before the N here. That's why. So just that, yeah, but this doesn't make a lot of sense. Yeah, so it's saying that before the N there on the function. So before here, you need to write mutable reference. Just kind of confusing to be honest, because by the type it kind of implies that it's mute. But whatever. Next one.
Yes, the key distinction is between same bucket and same key. A hash collision means two different keys produce the same bucket index. The code therefore walks the linked list in that bucket and asks, Rust if node.key key that check is not asking, did a collision happen? It is asking, is this exact key already present in the map? If the key already exists, a hash map normally updates its value rather than storing a second entry for the same key. For example, Rust map.insert foo 10 map. Insert foo 20 you don't want, bucket 3, foo 10 foo 20 you want, bucket 3, foo 20 and insert returns the old value 10. That is what this does. Rust returns some stdem replacement node.value. Value replace effectively performs old node. Value node.value value return old without illegally moving node.value directly out of a mutable reference. What happens during a real collision? Imagine these two different keys both map to bucket 5. Hash cat 16 5 hash dog 16 5 suppose cat already exists. Bucket 5 key cat value 100 next. None now you call. Rust map.insert dog 200 the code computes. Rust let itself to bucket underscore index key so idx 5 then it starts walking bucket 5. Rust let the curve bucket. As underscore while it's on node curve node.key key. Curve node next as underscore my first node. Key cat key dog cat dog regular arrow false so it keeps walking. Eventually, curve meaning I searched the entire collision chain and didn't find this key. Only then does it create a new node. The unsafe block step by step is the interesting part. Rust unsafe let bucket mud self to buckets to add idx remember. Rust self. Buckets is Rust mud option box node k. V conceptually the allocation looks like self to buckets bucket 0 bucket 1 bucket 2 bucket 3. Each bucket contains Rust option box node k. V so this Rust self to buckets to add idx is pointer arithmetic. If self to buckets address of bucket 0 idx 5 then Rust self. Buckets to add 5 gives a pointer to bucket 5. Conceptually, base pointer b0 b1 b2 b3 b4 b5. At 5 then Rust self to buckets to add idx here ranks that raw pointer. And Rust mud self to buckets to add idx creates an ordinary mutable Rust reference to that bucket. So after Rust let bucket mud self to buckets to add idx you effectively have Rust bucket mud option box node k. V from this point onward, most of the code is actually ordinary safe Rust operations. The unsafe is needed because Rust cannot prove that Rust idx self to cap and that self to buckets points to a valid allocation. Those are invariants the implementation itself promises. Then this happens Rust let curve bucket as underscore mud bucket is Rust mud option box node k. V calling Rust as underscore mud turns it conceptually into Rust option mud box. Node k. V so if the bucket is empty, bucket none curve none if it contains a linked list. Bucket some box node then curve some mud box node walking the collision chain then Rust while it's some node curve. Conceptually, bucket cat dog fox curve visits. Cat downward arrow fox downward arrow none at every node. Rust if node. Key means is this key being inserted already present? There are two possible outcomes. K say same key exists suppose inserting Rust insert dog 999 while bucket 5 cat dog. Fox upward arrow found then Rust node.key is true. So Rust stdem replace mud node.value value changes dog 200 into dog 999 and returns Rust some 200 no new node is added. Self.len therefore does not change. That's why there's an early Rust return inside the loop. Case B different key same bucket suppose inserting wolf and it happens to hash the same bucket cat dog. Fox the loop sees cat wolf dog wolf fox wolf eventually Rust turn on now the code knows wolf does not currently exist so create a new node. Here's another important detail. It does not append to the end you mentioned. Add a new value to the end of the linked list. This implementation doesn't do that. It inserts at the front. This code Rust lets old underscore head bucket takes the existing linked list out of the bucket. Before bucket cat dog fox after Rust lets old underscore head bucket. Take you temporarily have bucket none old underscore head cat dog fox then Rust bucket some box new node key value next old underscore head creates wolf next cat dog fox and puts that into the bucket wolf cat dog fox so collisions are handled through head insertion not tail insertion. That's usually simpler for a singly linked list because adding to the front is 1. Appending to the end would require traversing the list again or maintaining a tail pointer. Why search first if we're going to insert at the front anyway? Because a map has the invariant 1 logical entry per key not 1 logical entry per insertion consider Rust map. Insert x 1 map insert x 2 map insert x 3 if you blindly handle every same bucket occurrence as a collision you get x3 x2 x1 then what should Rust map get x return probably the first one it finds 3 but now your map contains duplicate keys and len 3 even though logically there is only one mapping. That's not normal hash map semantics. Instead insert x 1x 1 then insert x 2x 2 then insert x 3x 3 and len 1 the 3 situations to mentally separate this is probably the most useful. Mental model 1 different bucket hash a cap 3 hash b cap 9 no interaction whatsoever. Bucket 3 a bucket 9 b2 same bucket different key this is a hash collision hash a cap 3 hash b cap 3a b store both bucket 3 b a 3 same bucket same key this is not treated as another map entry but update the existing mapping before a 10 insert a 20 after a 20 return Rust some 10 you can therefore read the entire unsafe block is. This algorithm find the bucket for this key walk every entry already in that bucket. If one has the same key replace its value return the old value if we reach the end. This key does not exist create a new node make the old collision chains next make the new node bucket head increase len or visually hash key bucket 5 key target yes replace value no next node none insert new head so your intuition about the linked list is right. The list exists specifically to hold entries whose keys land in the same bucket. The equality test is necessary to distinguish genuine collision different key same bucket from an update same key same bucket.
Oh, I understand now. So yeah, I was conflating because it is kind of confusing. But let's say you want to update the value. So the loop is the collision. So this is the thing that was kind of confusing because when it said that it is to update the value, then I thought I was conflating the buckets with the actual value of the key on the hash map. actually updating the value on the hash map for the same key. And I thought I was conflating that with the bucket collision, but that's not what's happening. Is that this is actually for the bucket collision, but this is when you want to update the same key for the bucket collision. So let's say, for example, you add a value to the hash map that has the same bucket as another one that already existed on that space. Then it's gonna create a linked list for the same address in memory, but then it's gonna create another key on that place. But then let's say you wanna update the value of that key is connected to, then that's when it's gonna do this operation here. It's traversing the linked list to update a value of an existing key on a bucket that has a collision. That's what's gonna. And I think that this adds a new value. If the bucket is the same but there are no keys there yet, then there are no keys equal to this one that you wanna add, then does this. So the key is actually the value you're using to add to the hash map. It's not the value of the address. The value of the address is the bucket. It gets the index from here, which does the hash. So you pass the key, you get the hash, which is the address value, I think. And then it adds to these buckets here, which is linked list, I think. Yeah, it's a linked list of nodes. That's what's going on. That makes more sense. So I think I understand. I'm just gonna ask for line. I don't think I'm gonna ask questions about the other quiz there. They cannot move out of referencing. Okay, so it's here. It's trying to clone the value of this one. I think I remember this one. I think this is the answer. And it's because of the sort here. And because this is not mutable, then when it tries to sort, it would change the values on the array, which makes the thing break. I'm pretty sure that's the answer. Yeah, that's basically what I saw there. So this is it's printing based on the size. So this is a quiz about the zero size type variables, I think. Yeah, I think it's zero size type. There's this other concept which is zero cost abstraction. What that basically means, from as far as I understand, is that in Rust, whenever you have these generic types, the compiler is gonna figure out what type they should be whenever possible, I think, and then it's gonna create all the variations of that generic on compile time. So it's zero cost because on run is not figuring out the type on runtime. And zero size type, I don't remember really well. We'll search. What does it mean? Obviously, I think is that, as the name implies, it doesn't have a Like types that don't have a size. Yeah, no memory space, but so maybe I think that the reason why this exists is to allow the compiler to verify the type, but without using memory. So it doesn't require allocating anything in memory, but it's useful because it lets the compiler do checks, I think. That's why it exists probably. Just creating a reference to this. Then it passes this A here. This is basically what is the size of this. I think that's gonna be 0 probably. Not really sure. And I think the clone is 1 probably. Because it's gonna be bigger than the reference. I think reference is a 0 size type probably. I have no idea though. I think this is gonna be 0, 0 on this two. And then it's gonna be 1 and 1 for these ones. So I got 2 wrong. The first and the third, I think. Yeah, the first and the third. So the only one that is 0 size type is the fourth one. Because a reference is a reference and clones are 1. But then this one, so when you, because this one is special, this like thing here. I think when you clone, the reason why is because you're gonna get only the thing without the reference probably. And this parenthesis here without nothing is a 0 size type. I think that's why it's 0 here and the other ones are all 1. Because the address is gonna be 1. Then the clone of the variable is gonna be 1, regardless because we have the variable. Yeah, and produces the parentheses. Okay, so next one. So usually, from what I've seen, the 0 is gonna be the first variable inside of the struct, I think. So this is an empty struct. Which is initialized with i32. It passes 1 here. So I think it's checking to see when it's gonna drop the variable. So I think for the first one, it's probably gonna drop here. It's gonna be 1, the first. Then B drops here, I think. Actually, I'm not really sure though. I know this one here, it drops automatically. Or maybe this is an error, I don't know. Actually not, I don't think it is an error because it's gonna move the ownership on the first one. And because it doesn't use A after that, there's no problem. think it's just gonna be one, the print. I don't see why it would be anything else. But there's probably a trick here that I'm not sure. Yeah. So it's basically trying to explain exactly what I said there. So if you use the A after that, then you're gonna. And this one I already seen, I think last time that I did this, and it's not gonna be an error because it doesn't. When you push, it doesn't force resizing, so it doesn't change the. So what is happening is that it creates a vector of capacity, and then it use the capacity here, and then it pushes this value to the array. But since the capacity is 4 and is not filled, it doesn't go over the capacity when you push this value here, then it doesn't resize, doesn't reallocate the memory for the vector. It doesn't create a undefined behavior. But if it does resize, then you have undefined behavior, and then this becomes dangerous. You would be dereferencing a dangling pointer, I think. So the answer is going to be 0 here because it is the first element from what I remember. Okay. This one I also remember doing, but I forgot there's something about the lifetimes here that this was testing. I think it is an error. The first, from what I vaguely remember, the first one is correct because it uses this lifetime here. But then the second one, it doesn't work because the static doesn't work with this. Like, I don't remember really well. I think the issue is with this thing here because of the type here. I think it is an error, but I'm gonna ask GPT about this. Yeah, monomorphization is the name of the thing that I was talking about, where the compiler is going to replace the types. And I think the lifetime, based on this, so it at compile time, it defines the generic types and the lifetimes. And then it replaces them with the actual like concrete implementation so that at runtime we don't have the cost of converting.
Which is where the term higher rank comes from. The syntax to express HRTB for lifetimes uses the for keyword. To express the type of M1 above, we can have written let M1, M before RF and RM you can. Think of this as meaning, there is a lifetime but we don't need to know what it is just yet. Late bound lifetimes are always unbounded. There is no syntax for expressing a late bound lifetime that must outlive some other lifetime. Error. Lifetime bounds cannot be used in this context. SRC main ars 5:25 let underscore 4b. FND lifetimes on data types are always early bound except when the developers explicitly use the HRTB for syntax. On functions, lifetimes are late bound by default but can be early bound if the lifetime is declared outside the function signature. G an associated method of struct could be from the struct itself, or the lifetime parameter is bounded below by some other lifetime that it must outlive. As we've seen, this constraint is not expressible in the HRTB that would be involved in late binding the lifetime. By these rules, the signature FNF has a late bound lifetime parameter while the signature FNG has an early bound lifetime parameter even though the constraint here is ineffectual. Ordinarily these distinctions are compiler internal terminology that Rust programmers are not intended to know about or think about in everyday code. There are only a few edge cases where this aspect of the type system becomes observable in the service language, such as in the original quiz code. Back home, try again next quiz.
It's cheating. Hmm. So this is confusing because it's saying it compiles. There. Yeah, so GPT is wrong. Kind of weird because it ran the code there. Not sure what's going on. But obviously, I can't trust the answer, so it still should be interesting to see what it says. Yeah, so I think that this it just has more to do. To me, the weird thing that I don't understand very well is the syntax here. I do not know, like I don't know what this means necessarily. But I think the error here is because the static lifetime, it means that you're telling the compiler that the thing is gonna live throughout the whole lifetime of the program. But when you put a generic lifetime here, is like on a smaller subset than the static lifetime. So it basically contradicts itself. So you're saying that this is gonna live forever, but then here you're saying that it might not live forever. So
It compiles. It is not undefined behavior, but the output is not reliably determined. It may print either 0 or 1 depending on how the compiler /code gen handles the two functions. Here's why. Rust fnf, fng, a, the bound on g, rust, a means that outlives itself, which is trivially true. So semantically these functions do essentially the same thing, nothing. Also, these lifetime parameters are early bound here, so spelling, rust f, static g, static is permitted. Lifetimes don't become runtime data, they're erased during compilation. Rust reference distinguishes early bound lifetimes as part of a function item identity, but once you coerce each function item to fn, you're dealing with function pointers. Rust documentation plus one of the crucial lines are rust lit pf, static asm lit pg, static asm before the casts, f, static and g, static are different function items because they're different functions. After rust asm you have pf, fn pg, fn then, rust pf pg compares function pointers, and rust explicitly warns that function pointer equality is unreliable. Different functions can have the same address if the compiler /link converges identical functions, while the same function can even have different addresses in different code gen units. Rust documentation plus one, so these two empty functions, rust fnf, fng, a, might be emitted separately. F address 0x1000 g address 0x1100 pf pg downward arrow false false is 0 giving 0 but the optimizer slash. Linker can notice that their machine code is identical. F, retg, ret and merge them. F address 0x1000 g then, pf pg downward arrow true true is 1 giving 1 in fact. Current rust has a warn by default link specifically for this unpredictable underscore function underscore pointer underscore comparisons because different functions may share an address after duplication. Rust documentation plus one, so the quiz answer question answer does it compile? Yes, is there UB? No, does it necessarily print 0? No, does it necessarily print 1? No possible output 0 or 1 y. Function pointer identity is not guaranteed to correspond 1 to 1 with rust function identity. The especially tricky lesson is that rust f g at the function item identity level does not imply rust fast. Gas at the machine code address level. So if this is a quiz expecting one exact output, either 0 or 1, function pointer comparison is intentionally unreliable is the strongest answer.
yeah, so I'm gonna stop streaming here. Next time, I think I'm just gonna continue to do this thing here, or some variation of this. Maybe I'll do LeetCode or Codeforces again, as well. I'm thinking about whether or not doing that. So see you next time.